Okay, so today we're going to talk about Metal Activity Series. And hopefully we're going to get a pen that writes here. Okay, good. Metal Activity Series. So we all know that we're studying Redox right now. And we should at this point understand that metals tend to donate electrons. In other words, they are reducing agents, okay? And they tend to donate their electrons over to oxidizing agents. Well, it turns out that if you compare the metals to one another, they're not all going to have equal abilities to, if you want to think about it, push their electrons onto other species. So to start off, you see this little picture here. And this is an experiment we just did. In the first case, we took silver nitrate solution, and we put a strip or a wire, a copper wire in here, a corkscrewed copper wire, and we witnessed that all of a sudden this silvery crystalline substance, which is elemental silver, began to collect onto this copper wire. And then we took copper sulfate solution, and we placed a strip of zinc in, and we noticed that very black color got deposited on the zinc, which turns out to be elemental copper being reduced onto the zinc plate. So we're going to write a couple of reactions and just look at what's going on here. So in the first case, we have a solution of aqueous silver nitrate. Okay, and so what that means is, if this is a test tube and there's nothing in it but silver nitrate, okay, we're going to have positive silver ions present in the solution. Okay, and if we were to take a copper strip or copper wire, place it in there, okay, so this is made of solid copper, so a strip of solid copper, you'll see that silver starts to deposit onto the copper. So what must be happening, right, for silver to come out of solution, it must be being reduced to elemental silver. In other words, copper is donating electrons to the silver and causing it to deposit onto this strip. So let's look at that process a little more closely if we can. It's really hard to draw straight lines. I should use a straight line tool. So here's copper. And copper can form either copper 1 or copper 2 ions. We'll assume that it's forming copper 2 ions. I'm not sure exactly how you tell which way it's going, but what happens is some of these silver ions here come in contact with the surface. And when they do so, what ends up going on is electrons that were in the outer shell of copper pass into the silver, okay, and that silver is now reduced to elemental silver. So if you want a little equation for that, what we can say is we can say that two silvers plus, two silver pluses plus 2 electrons become 2 solid silvers at the surface. The consequence of this is that we now release copper ions, right? After these electrons have left copper, what we have is we have copper 2 plus ions that then dissolve out into solution. You'll notice back in this picture that the liquid is turning blue, right? Blue is an indicator of the presence of copper ions. So you have this kind of redox reaction between copper and silver, and what that means is that copper is able to reduce silver. Silver cannot reduce copper. So if I did this in reverse, if I had a solution of copper ions and I placed silver in there, nothing would happen. Silver is not as reactive as copper, and therefore this is only going to work in this one direction. So let's just write out the whole equation and check out its parts, okay, and identify how it's redox. Don't worry about this for now. We'll look at this in a second. Okay, so what we have here is we have solid copper plus 2 silver ions, and from that we get 2 silver molecules, or sorry, I should say silver atoms, and 1 copper ion. Okay, or a cupric ion if you want. And breaking that apart, okay, if you look up here, silver is receiving 2 electrons, and if we look at copper, if we want to see that part of the reaction, we have copper producing Cu2 plus 2 electrons down here. Okay, so in this case, what we've got is we've got copper reducing silver. In the second part of this reaction, we have zinc reducing copper ions. So let's just quickly look at what's going on there. Let's get the pen out. So what we have is we have another test tube, and in this test tube we have some copper sulfate. Okay, so in that case we've got the 2+ version of copper. So we'll put them in there. And into that we place zinc. And it turns out that zinc is a much more active metal, or a much stronger reducer than copper. And that zinc is capable of pushing its electrons off onto copper. I think zinc is a 2+, but let me double check. It might not be. Yeah, it is. Okay, perfect. So what we've got going on here is we've got solid zinc. We've got copper ions. And what we end up with is we end up with zinc ions, and we end up with solid copper. Okay? And you can see that solid copper as that black tarnish on our zinc strip. Okay, so there it is down there. All right. So what we can do is we can use this process. Yes, I have a student with a question. Yes. Why is it bubbling so much? Good question. I'll have to look into it. Okay. Let me just finish what I'm talking about, though. So what we can do with this type of reaction is we can take solutions of various metals and we can place other solid metals in them. We can essentially see which metals are able to reduce which metals. And over time, what you can do is you can build what's called an activity series. Okay? So if you take a look at this activity series, what it's showing you is it's showing which metals are the best at pushing their electrons on to other metals. All right? So what we're basically saying here is, I mean, some of these you can't really do a reaction of the same kind that we have here because they would react with the water itself. But let's just consider what this all means here. So if you look right at the top, we have potassium. And what this is saying is that potassium is capable of pushing its electrons onto the ions of anything down this list. All right? So we had a solution of sodium ions. Potassium should be able to reduce sodium. In other words, push its electrons onto sodium and reduce sodium out of solution. Now that's not a very realistic situation, but if we come down here to, say, magnesium, which doesn't react with water, okay, magnesium should be able to reduce any metal that's below it on the activity series. So let's find the metals that we used. We had zinc metal, and we used zinc metal to reduce copper ions. And so if you look, since zinc is way up the activity series, way above copper, this makes a lot of sense. Okay. We also took copper metal, which is here, and we used it to reduce silver ions to silver. Okay. So this is a handy little chart that essentially just shows the reducing power of different metals, how capable they are of pushing electrons onto other metals. Okay. Now you might be thinking to yourself, well, where are we going with this? Well, the first place we're going is we're going to be able to predict whether certain reactions are going to be able to occur. Okay, so let's think about some reaction that we can use as an example. Okay, so I've written 2 reactions down here, and the question that we're going to ask is, will these reactions occur? So, will this first reaction occur? Will silver be able to reduce the zinc ions from this zinc chloride? If we look at the activity series, what we got to see is silver above zinc? And I think we probably already know that it's probably not going to be, right? Zinc's way up here, if you look, and silver's way down here. So in this first case, silver will not be able to reduce the zinc ions, and this reaction won't occur. Does that make sense? So we can use the activity series to predict whether reactions occur, and this one will not. No, silver, Ag, can't reduce zinc. So what we would say is, a way to say this is we would say silver is less active than zinc. So silver is less active than zinc. Now let's look over here. Okay, so we have iron 3 ions in solution, right? So remember, if we look at this, one thing that's kind of helpful, which I should have done, is put the state in, right? So it's aqueous, it's dissolved. This would be solid. We want to know if magnesium can reduce iron ions. So in solution, we'd have 3 pluses, and what we're saying is, can magnesium push its electrons onto this iron and thereby reduce it? Can magnesium reduce iron? Is magnesium a stronger reducing agent than iron? We roll up. Yeah, there's magnesium. And down the list is iron. So absolutely, magnesium will be able to reduce iron. Okay? Does this make sense? So let's just analyze this reaction a little bit more closely and see what's happening in terms of oxidation numbers. Okay? So, that. So if I'm looking at this, what is the oxidation number on iron over here? Who can tell me? Don't be shy. +3. Remember, oxidation numbers are +3 rather than 3 plus. That's the ion charge. The ionic charge is +3, and it matches the oxidation number. Okay, we got negative there, -1. We've got 0 on magnesium. Okay, then we've got a +2 on magnesium over here. This is still negative, and we've got a 0 on iron. Okay, so iron is reduced, and the agent that reduced it is magnesium. So magnesium in this situation is acting as the reducing agent. Okay, so magnesium reduced iron. Okay, in the process, magnesium itself is what? Oxidized, right? It's oxidized. So magnesium goes from 0 to +2. It's oxidized. So in this case, you can consider iron to be an oxidizing agent. Is iron always going to be an oxidizing agent? Absolutely not. If you react, iron metal with something that's below it on the list, like, say you had copper ions in solution, well, it turns out that iron would be capable of reducing the copper ions. I used zinc, but I could have just as easily used iron, and we've got a similar result on that. Okay? So what we're basically saying here is we're ranking metals in terms of their ability to reduce other metals. Okay? The strongest reducing agents are found on the left high side of the periodic table. Can anyone explain why that's the place you're going to find your best reducing agents? Why are the alkali metals towards the top left of the periodic table? Why is that? Yeah. Not electronegative. It does have to do with electronegativity, but we would not consider them to be highly electronegative. In fact, just the opposite. Yes, Jesse. Right? So they have 1 electron in their outer shell. And sorry, I kind of didn't say that right. What should be happening here, although it doesn't follow this perfectly, is I guess generally we would think that the more reactive the metals are, the better they are at being reducing agents. Well, that doesn't exactly bear out here. I think this maybe has something to do with reduction potentials, but essentially the concept is that these have single electrons in their outer shell, right, as was mentioned. As you go down, there's more shielding, and those electrons are farther away from the core, and therefore more easily, if you want, released or pushed off onto other metals, or even onto oxidizing agents such as oxygen and chlorine and so on. So this is kind of the concept, and this is bringing back in some earlier chemistry that we did when we examined the trends in alkali metals and alkaline earth metals and so on. So you'll notice alkali metals tend to be able to reduce alkaline earth metals, and alkaline earth metals tend to be able to reduce metals that are farther to the right. And your non-reactive metals like gold and platinum are way down at the bottom of the list. They're not considered very active. And in fact, something like gold can be exposed to oxygen and it will not give up its electrons readily to oxygen. So things like gold and platinum don't tarnish, whereas, over time silver will tarnish. It's generally, I don't think tarnishing because of oxygen in the air. I think it's actually acting with sulfate or sulfur. Copper tarnishes and turns green over time, and so on. Metals that are up here are not used for the same things that metals that are down here, right? These are the coinage metals, and just the fact that they are not highly reducing or highly reactive or highly active gives them those desirable properties like being coins or being carved into jewelry and so on, right? Jewelry made of zinc or iron or whatever or or sodium is not going to be very desirable because it's going to react with everything around it in the world. So you can see here on this little chart how reactive they are with common substances. So the alkali metals and some of the alkaline earth metals will react readily with water. As you go down, they'll react with acid, and then some down here won't even react with acid. Interestingly, this is the reverse order of how easy they are to get. Okay, so since something like gold is not reactive, what that means is if you have some ore with gold in it, essentially all you have to do is put that rock in a fire. The gold will heat up and melt and dribble out of the rock, and it can be collected. So metals that are down here historically were some of the first ones to be discovered because it's pretty easy to obtain them from their ores. Whereas as you go up, something like iron, for instance, is a little bit more difficult to get out of its ores. You have to actually find a way to reduce it. And one way is they smelt it with carbon or coke. Okay, and then ones that are way up here, if you want to get some sodium, I'll just say sodium chloride, for instance, you're going to need to apply very strong electricity and electrical currents, and you're going to have to actually pull it out of its ionic form. All right, so it's kind of an interesting, historical situation. You'll also notice that these still have their Latin symbols, and that's because of this fact that they were able to be, collected simply by throwing ore into fire and waiting for the metal to melt out of there, rather than the complex techniques that you need to, say, get something like aluminum or some of these more reactive metals. Okay, and that's it for today.